Hello friends, welcome to my lecture on residue theorem. We will first determine the residue in the case of a simple pole. There are methods which we can use to determine the residue in the case of a simple pole. Okay. So, let us first discuss a method where we will be able to find the residue in the case of a simple pole. If Fz has a simple pole at z equal to z naught, then the Lorentz series of Fz is of the form Fz equal to sigma n equal to 0 to infinity Bn z minus z naught to the power n plus C1 over z minus z naught, and 0 is less than mod of z minus z naught less than r. Because the function Fz has an isolated singularity at the point z equal to z naught. So, there exists a neighborhood, a deleted neighborhood of z equal to z naught in which the Laurent series converges. Now, this Laurent series can be put in the form z minus z naught into Fz equal to sigma n equal to 0 to infinity Bn z minus z naught to the power n plus 1 plus C1. We can multiply this equation by z minus z naught. Now, then if we take the limit of z tends to z naught, then limit z tends to z naught, z minus z naught into Fz will be equal to limit z tends to z naught sigma n equal to 0 to infinity Bn z minus z naught to the power n plus 1 plus C1. But here we see that each term contains z minus z naught as a factor. Even the first term, when you put n equal to 0, is B naught into z minus z naught. Okay. So, each term here contains z minus z naught as a factor. Therefore, when we take the limit as z tends to z naught, this part on the right side will tend to 0, and so right side will tend to C1. Okay. And so, C1 will be the limit of z minus z naught into Fz as z tends to z naught. Okay. So, C1 we know the C1 is the coefficient of 1 over z minus z naught, and therefore, C1 is the residue of Fz at z equal to z naught. So, when we want to find the residue C1, okay, of a function Fz in the case of a simple pole at z equal to z naught, we do not need to write the Laurent series for the function Fz with center at z equal to z naught. We can directly use the formula to evaluate C1. The formula is C1 equal to limit z tends to z naught, z minus z naught into Fz. In the case of a simple pole, there is another useful formula to determine the residue at the point z equal to z naught. Let us see the other formula. If Fz has a simple pole at z equal to z naught, then we can write Fz as Pz over Qz, where Pz and Qz are analytic at z equal to z naught. Pz naught is not equal to 0, and Qz has a simple 0 at z equal to z naught. Okay. So, Qz has a simple 0 at z equal to z naught means Qz naught is equal to 0 and Q prime z naught is not equal to 0. Okay. So, if Qz has a simple 0 at z equal to z naught, then Qz naught is equal to 0 and Q prime z naught is not equal to 0. Now, Qz is analytic and has a simple 0 at z equal to z naught. So, Qz can be expanded in a Taylor series of the form Qz equal to this. Okay. Here the first term Qz naught is not written because Qz naught is equal to 0. So, Qz equal to z minus z naught, Q prime z naught, z minus z naught whole square by 2 factorial, Q double prime z naught, and so on. Let us put this value of Qz in the denominator here for Qz. Then we see that C1 we have seen in the case of a simple pole, C1 is given by limit z tends to z naught, z minus z naught into Fz. So, limit z tends to z naught, z minus z naught into Fz is Pz over Qz. So, this is the expression for Qz. Okay. We can write the expression for Qz as z minus z naught times Q prime z naught plus z minus z naught by 2 factorial Q double prime z naught, and so on. So, that we have written here. Now, z minus z naught we can cancel, and then as z tends to z naught, Pz goes to Pz naught because Pz is analytic. Okay. So, Pz and therefore, it is continuous. So, Pz naught, and similarly Qz is analytic. So, it is continuous, q prime z is also analytic, so q prime z is also continuous. So q prime z naught we get, so p z naught over q prime z naught. Now so this formula is also sometimes useful to determine the residue in the case of a simple pole at z equal to z naught. For example, suppose we have this function f z equal to z to the power 4 plus 1. Now this function has got poles at the points where the denominator of this f z vanishes. Okay. So z to the power 4 plus 1 equal to 0. Z to the power 4 plus 1 equal to 0 gives us z equal to minus 1 to the power 1 by 4. Now we know that minus 1 lies here on the real axis, and its magnitude minus 1 if you write in the polar form, then minus 1 is equal to mod of minus 1 into e to the power theta, where theta is the argument of minus 1. So this argument is pi, so we have e to the power I pi. So minus 1 is e to the power I pi. So this is equal to e to the power I pi raised to the power 1 by 4. Now we can write its general value e to the power I pi plus 2 n pi I divided by 4, where n takes value by de Moivre's theorem. So applying the de Moivre's theorem, the 4 roots of minus 1 to the power 1 by 4 are given by e to the power I pi plus 2 n pi I by 4, where n is equal to 0, 1, 2, 3. That means that when you put n equal to 0, you get e to the power I pi by 4. Let us call it as z1. Now z2 is e to the power 3 I pi by 4, which you get by putting n equal to 1 here. When you put n equal to 2, you get z3. z3 is equal to e to the power 5 I pi by 4, 5 I pi by 4, and then z4 equal to e to the power 7 I pi by 4, which you get by putting n equal to 3. Okay. Now let us plot these 4 roots z1, z2, z3, z4 in the Argand diagram. Okay. So if you draw them in the Argand diagram, since the modulus of z, mod of z is equal to 1, okay, z is minus 1 to the power 1 by 4, mod of z is equal to 1. So all the 4 roots lie on the unit circle. Mod z equal to 1. Okay. The first root is z1 equal to e to the power I pi by 4, so it lies here, e to the power I pi by 4, its argument is pi by 4 and absolute value is 1. Okay. Then the second is e to the power 3 I pi by 4, it lies here. This is 3 pi by 4 angle. Okay. This is 3 pi by 4 angle, and then e to the power 5 I pi by 4. So it is e to the power 5 I pi by 4. Okay. So this is this one, e to the power 5 I pi by 4, and this is e to the power 7 I pi by 4. Okay. This is z4 and this is z3. Now z3 can also be written as e to the power minus 3 I pi by 4, okay, because e to the power 5 I pi by 4 e to the power 5 I pi by 4 plus 3 I pi by 4 minus 3 I pi by 4 gives you e to the power 5 I pi by 4 plus 3 I pi by 4 is 8 I pi by 4. So e to the power 2 pi I and then into e to the power minus 3 I pi by 4. E to the power 2 pi I equal to 1. So we get e to the power minus 3 I pi by 4. So z3 is also equal to e to the power minus 3 I pi by 4. Okay. And similarly z4 is e to the power 7 I pi by 4. So here also let us add I pi by 4 and subtract I pi by 4. So this is e to the power 8 I pi by 4 means e to the power 2 pi I into e to the power minus I pi by 4, and we get e to the power 2 pi I is 1. So we get e to the power minus I pi by 4. Now let us find the there are 4 factors of Z4 plus 1. Fz we can write as 1 over Z minus Z1, Z minus Z2, Z minus Z3, Z minus Z4. Okay, where let us recall Z1 is e to the power I pi by 4, Z2 is e to the power 3 I pi by 4, Z3 is e to the power minus 3 I pi by 4, and Z4 is e to the power minus I pi by 4. Okay. Now, suppose and okay, so and at each of these points, okay, Z1, Z2, Z3, the denominator has a simple 0, okay, and therefore Fz has simple poles at Z equal to Zi, I equal to 1, 2, 3, 4. Now, if you want to determine the residue at Z1, Z2, Z3, Z4, okay, and you apply the first formula. The first formula was C1 equal to limit Z tends to Z naught, Z minus Z naught into Fz, okay. To determine the residue in the case of a simple pole at Z equal to Z naught, if you apply this formula, okay, to determine the residue at the point Z equal to Z1, from here what we get? Residue at Z equal to Z1 of Fz will be equal to limit Z tends to Z1, okay, and then Z minus Z1 times Fz. So, this will give you what? Limit Z tends to Z1, Z minus Z1 into 1 upon Z minus Z1, Z minus Z2, Z minus Z3, Z minus Z4. Okay. We can cancel Z minus Z1 in the numerator and denominator, and then we have Z1 minus Z2, Z1 minus Z3, Z1 minus Z4. Okay. So, this is the residue at Z equal to Z1. Okay. Similarly, residue at Z equal to Z2 if you find, then we have limit Z tends to Z2, Z minus Z2 into Fz, and what we get now? We have 1 over Z minus Z2 will now cancel in the numerator and denominator. So, we will have Z2 minus Z1, Z2 minus Z3, Z2 minus Z4. Okay. Let us first see how difficult it is to determine the residue at Z equal to Z1 and Z equal to Z2 here. You have to put the values of Z1, Z2, Z3, Z4 here, and then you have to multiply them, and then you have to find 1 over Z minus Z1 minus Z2, Z1 minus Z3, Z1 minus Z4. So, it is not easy to determine the values of the residue of Fz at Z equal to Z1 and Z equal to Z2. If you apply the other formula is C1 equal to Pz naught over Q prime Z naught. Okay. If we apply this formula, then you will see it is easy to determine the residue at each one Z equal to Z1, Z equal to Z2, Z equal to Z3 and Z equal to Z4. What we have to do is simply we have to differentiate the denominator. Okay. Fz is 1 over Z to the power 4 plus 1. Here we had taken Fz as Pz over Qz. If Fz is Pz over Qz, then we know that C1 is equal to Pz naught over Q prime Z naught. Denominator only we have to differentiate. So, here this will be 1 over 4Z cube. Okay. And so, the residue at Z equal to, so residue at Z equal to Z1 will be of Fz will be 1 over derivative of the denominator, that is 4Z cube, and you put Z equal to Z1 and you get 1 over 4Z1 cube. Similarly, if you find the residue at Z equal to Z2, You do not have to do anything, you know already the derivative of the denominator of f z. So, again 1 by 4 z cube and you put z equal to z 2. So, this is 1 over 4 z 2 cube, and similarly for z equal to z 3 and z equal to z 4, we will get the residue as 1 over z 3 cube, 1 over 4 z 3 cube and 1 over 4 z 4 cube. Okay. And so, here it is, you can see very easy, 1 by 4 z1 is e to the power I pi by 4. So, we get e to the power 3 I pi by 4. Okay. And if you multiply by e to the power I pi by 4 in the numerator and denominator, what we get? E to the power 4 I pi by 4 means e to the power I pi, e to the power I pi equal to 1, e to the power I pi is minus 1. So, minus 1 by 4 e to the power I pi by 4, and here what we get 1 by 4 e to the power 3 I pi by 4 to the power 3. So, that means 9 I pi by 4. So, we get 1 by 4, this is e to the power 2 pi I into e to the power I pi by 4, e to the power 2 pi I equal to 1. So, we get 1 by 4 e to the power minus I pi by 4. So, you can see it is very easy to determine the residue if we differentiate the denominator and put the the value of z. Okay. Like, but here if you find the residue using this formula, then it is not easy to determine, because you have to put the values of z1, z2, z3, z4, then you have to multiply them and then you have to find the reciprocal of that. So, it is easy to determine this. We use this formula, this one, okay, this formula we use when z minus z naught is given as a factor of f z. Like say we will see some examples later, there it is better to use this formula, not this one. Okay. So, we will see a problem like that. So, but here in this particular problem where f z is 1 over z to the power 4 plus 1, we need to use this formula to obtain the residues easily. Okay. So, this formula is very useful in some cases. Now, let us consider the residue of f z in the case of a pole of order m greater than 1. If f z has a pole of order m, say greater than 1 or greater than or equal to 2, let us say m is greater than or equal to 2 at a point z equal to z naught, then the corresponding Lorentz series expansion is of the form f z equal to sigma n equal to 0 to infinity b n z minus z naught to the power n, c 1 over z minus z naught, c 2 over z minus z naught square and so on, c m over z minus z naught to the power m, where c m is non-zero and the region of convergence is 0 less than mod of z minus z naught less than r, because the poles are isolated singularities. Now, from this, when you multiply this equation by z minus z naught to the power m, what we get is z minus z naught to the power m f z equal to sigma n equal to 0 to infinity b n z minus z naught to the power n plus m, then c 1 z minus z naught to the power m minus 1, c 2 z minus z naught to the power m minus 2 and so on, c m minus 1 over c m minus 1 into z minus z naught, okay, c m minus 1 into z minus z naught plus c m. Okay. Now, this right hand side then is nothing but a power series in with center at z equal to z naught. Why? Because this is constant term, first term c m, then c m minus 1 into z minus z naught, then c 2 z minus z naught, c m minus 2 z minus z naught whole square and so on, c 2 z minus z naught to the power m minus 2, c 1 z minus z naught to the power m minus 1, and here we have b naught z minus z naught to the power m, b 1 z minus z naught to the power m plus 1. So, right hand side defines an analytic function, okay, that is z minus z naught to the power m into f z is an analytic function. So, the residue of residue c 1 of f z, okay, the residue c 1 of f z at z equal to z naught is now the coefficient of z minus z naught to the power m minus 1, okay. This c 1 is the residue of f z, okay, it is now the coefficient of z minus z naught to the power m minus 1, and as I said, the right hand side is the Taylor series, okay. This right hand side is the Taylor series of the function z minus z naught to the power m into f z, because it is a power series with center at z equal to z naught. So, let us call g z to be z minus z naught to the power m into f z, okay. So, right hand side, this one is the Taylor series of the function gz. We are calling this function as gz. Now we know that if gz is the if the right hand side is the Taylor series of gz, gz is equal to then sigma n equal to 0 to infinity g upon n factorial into z minus z naught to the power n. So, if we want the coefficient of z minus z naught to the power m minus 1 in the Taylor expansion of gz, then the coefficient of z minus z naught to the power m minus 1 in the Taylor series, Taylor expansion of gz is gm minus 1. Okay, you put n equal to m minus 1. So, gm minus 1 z naught divided by m minus 1 factorial. Okay. So, this C1, okay, this C1 is the coefficient of z minus z naught to the power m minus 1. So, C1 is gm minus 1 z naught over m minus 1 factorial. So, we get 1 over m minus 1 factorial. Now, gz is z minus z naught to the power m into fz. This is m minus 1th derivative of gz. We are writing limit z tends to z naught because fz has z minus z naught. I mean fz has a pole at z equal to z naught of order m. So, fz is of this form, okay, where z minus z naught occurs in the denominator. So, we are multiplying by z minus z naught to the power m. So, directly we cannot put z equal to z naught, we should take the limit as z tends to z naught. So, C1 is 1 over m minus 1 factorial limit z tends to z naught. This is m minus 1th derivative of gz. So, this is gm minus 1 z, okay, this is gm minus 1 z, okay, and we are finding the limit of gm minus 1 z as z tends to z naught. Now, let us consider this function fz equal to 2z over z plus 4 into z minus 1 whole square. Then you can see that fz has a simple pole at z equal to minus 4. And it has a pole of order 2 and a pole of order 2 at z equal to 1. We can see this easily if you recall the definition of a pole of order m. We had said that fz has a pole of order n at z equal to z naught if limit z tends to z naught z minus z naught to the power n into fz is equal to a, which is non-zero and finite. Okay. So, here you can see if you multiply fz by z plus 4 and take the limit as z tends to minus 4, okay, limit z tends to minus 4 z plus 4 into fz. Then what will happen? Fz z plus 4 will cancel and this will be equal to limit z tends to minus 4 and we will have 2z upon z minus 1 whole square. So, this will be equal to 2 into minus 4. So, minus 8 divided by minus 5 whole square. So, we get minus 8 by 25. Now, here in the case of the simple pole at z equal to minus 4, it is not advisable to use the formula for the simple pole residue at simple pole as residue at z equal to z naught of fz, which is given by p z naught over q prime z naught. So, it is not advisable to use this formula here, okay, because here if you differentiate the denominator and then put z naught means minus 4, then it will be a little bit cumbersome. If you multiply fz by z plus 4 and take the limit as z tends to minus 4, then it becomes easy to determine the limit. So, we have to decide from the definition of the function fz which formula for simple pole we have to use. to get the residue. Okay. So, now let us find the residue at the double pole at z equal to 1, okay, for this function. So, let us use we have f z equal to 2z upon z plus 4 into z minus 1 whole square. Okay. So, we are finding the residue of f z at z equal to 1. It has a pole of order 2. Okay. So, we have in the case of a pole of order m, the formula is residue at z equal to z naught f z. When f z has a pole of order m, it is m minus 1 over m minus 1 factorial limit z tends to z naught dm minus 1 over dzm minus 1 and then z minus z naught to the power m into f z. Okay. So, we apply that formula. So, here we have a pole of order 2. So, m is equal to 2. So, 1 over 2 minus 1 factorial, okay, limit z tends to z naught is 1. So, z tends to 1 d over dz, because m is equal to 2 d over dz. Then we have z minus 1 whole square for z minus z naught to the power m, we write z minus 1 whole square here into f z. F z is 2 z divided by z plus 4 into z minus 1 whole square, and we get 1 over 1 factorial is 1. So, limit z tends to 1 d over dz of 2z by z to the plus 4. Okay. So, we get limit z tends to 1, let us differentiate. So, we have derivative of 2z is 2 into z plus 4 minus derivative of z plus 4 is 1. So, we get 1 into 2z. So, we get this divided by z plus 4 whole square. So, limit z tends to 1 and 2z will cancel, we have 8 divided by z plus 4 whole square. So, 8 by 25. Okay. So, this is how we get the residue in the case of a pole of order m, where m is greater than 1. Okay. Now, let us go to the residue theorem. I mean, we are now going to discuss the residue theorem. We have seen how we can evaluate the contour integrals whose integrand has only one isolated singularity inside the contour of integration. There we simply find the coefficient the residue of f z at that point and then multiply by 2 pi I. Okay. Now, if your contour of integration has finite number of isolated singularities, then how we will extend that method. So, this theorem actually talks about that. So, let f z be analytic inside and on a simple closed path C except for finitely many singular points a1, a2, am inside C. Then if you find the integral of f z around C, it is 2 pi I into sigma j equal to 1 to m residue of f z at z equal to a j. So, let us say suppose this is your contour, okay, C, and you have singular points at a1, a2, a3 and so on am. Okay. These are isolated singularities of f z which occur inside C. Okay. Then how we will find the integral of f z around C. So, this theorem tells us that you find the residue of f z at each of these isolated singularities a1, a2, a3 and so on am, sum them up and then multiply by 2 pi I. Here integral around C is being taken in the counterclockwise sense. Now, what we do is we enclose the singularities m singularities C1, C2, Cm at A1, A2, Am within a small circle C1, C2, Cm. What we do? Let us take small circles. Okay, with center at A1, A2, A3 and so on Am. This is circle C1, this is C2, C2, this is C3, this is Cm. Okay. So, let us construct circles of sufficiently small radius with center at A1, A2, A3 and so on Am. we call these circles as C1, C2, C3 and so on up to Cm, such that the circles do not overlap and are completely inside the simple closed path C. Okay. So, we enclose the M singularities with the small circles C1, C2, Cm with their centers at A1, A2, Am respectively, with radii small enough such that the circles do not overlap and lie inside C. Then Fz is analytic in the multiply connected domain bounded by C and C1, C2, Cm, okay, and on the entire boundary of D. So, then we can see that then Fz is analytic everywhere inside this simple closed paths inside this C, okay, this region, I mean this region, this shaded region, it is analytic everywhere here, okay, as well as on C1, C2, Cm and the curve C. Okay. Now, what we do, we join these points, these paths by cross cuts. Okay. Let us draw another figure. Let me draw here. This is your C. Okay. This is A1, this is A2, this is A3 and this is Am, let us say. Okay. We draw small circles, we center at these points. Now, join them by cross cuts with the boundary. Okay. And then we can see that integral over C Fz dz plus integral over Cj, where j runs from 1 to m, summation over Cj j runs from 1 to m is equal to 0. So, by Cauchy integral theorem, let us show it here. So, let us draw a bigger figure. This is your contour C, okay. This is A1, A2, A3 and here let me write Am, okay. So, this small circle let us draw, okay, and then join them with the boundary of C, boundary C, okay. So, then what we do, let us start from here, okay. So, we start from this point, let me go this way and then when I reach here I come this way and then I move clockwise and then I go here and then when I reach here this point, okay, I go this way, then this and then this way, okay, and then I move on, I come here, I move this way, then clockwise, then this way and then this, okay, and when I reach here I move this way, then this and then this, okay, and I come back to the original point, okay, with which I started. Then you can see now the shaded region, okay, is bounded by this path, okay, which consists of C1, C2, Cm, C and the these things cross cuts. But you notice that along the cross cuts we are moving in opposite directions, okay. We are moving this way, then we are coming this way. So, integral along the opposite directions will cancel and then along C we are moving in the anti-clockwise direction, okay. So, integral over C Fz dz plus integral over C1, C2, Cm we are moving in the clockwise direction. So, integral over C1 Fz dz plus integral over C2 Fz dz and so on, integral over Cm Fz dz, okay, will be equal to 0 because the this path encloses a simply connected domain, okay. And so, integral along C is in anti-clockwise direction, while C1, C2, Cm, okay, integral along Cj j equal to 1, 2 and so on up to m, okay, is in clockwise direction. So, this equation then gives us integral over C Fz dz equal to integral over C1 minus integral over C1, okay, Fz dz minus integral over C2 Fz dz and so on minus integral over Cm Fz dz. Okay. So, this will give you integral over C1 plus integral over C2 and so on integral over Cm Fz dz, where now all the integrals, integral along C and integral along Cj, okay, j equal to 1 to 1 to 3 and so on up to m are in the anti-clockwise direction, because here these integrals were in the clockwise direction. When you put a negative sign, it and then this integral along anti-clockwise is equal to negative of integral over clockwise. So, this is now, so the integrals around C and Cj, j equal to 1, 2 and so on up to m are in anti-clockwise sense. Okay. Now, you can see that C1, C2, C3 and so on up to Cm, each one encloses just one singularity, singularity at A1, singularity at A2, singularity over A3. So, we know that integral over C1 Fz dz is 2 pi I into residue at z equal to A1 of Fz, and then integral over C2 will be 2 pi I residue of Fz at z equal to A2, and similarly integral over Cm Fz dz will be residue of Fz at z equal to Am. Okay. So, multiplied by 2 pi I. Okay. So, this is nothing but 2 pi I times sigma residue of Fz at z equal to Aj, where j runs from 1 to m. So, this is how we evaluate the integral of Fz around C. We simply find the residues of Fz at its isolated singularities at the points A1, A2, Am, and then sum them up and multiply by 2 pi I. So, we had this equation where the integral along C is anti-clockwise direction, while integral along C1, C2, Cm is in the clockwise sense. When we take these terms integral over Cj, j equal to 1 to 2 m up on the other side, we get the integrals along C1, C2, Cm in the anti-clockwise direction, and we get this result. Okay. Now, let us consider this function. We have Fz equal to e to the power zt over z square plus 2z plus 2. We have to find the value of this integral. C is the circle with center at origin and radius 3. Mod z equal to 3. Okay. Now, let us notice that here Fz is equal to e to the power zt over z square into this is z square plus 2z plus 2, and z square plus 2z plus 2 if you put equal to 0, then you get z equal to minus 2 plus minus under root b square means 4 minus 4ac means 8 divided by 2. So, we will get here minus 2 plus minus 4I plus minus 2I, okay, divided by 2. So, minus 1 plus minus I. So, the roots of the denominator, okay, denominator here is z square into z square plus 2z plus 2. The roots are z equal to 0 and z equal to minus 1 plus minus I. So, let us plot them. Z equal to 0 is here, minus 1 plus I, okay, minus 1 plus I is here, minus 1 plus I, this is minus 1 point. So, minus 1 point. Okay. So, this is one singularity and there is minus 1 minus 1. So, this is minus 1 minus 1. Okay. So, all the three, and now you can see the distance of minus 1 1 are minus 1 minus 1. Okay. Whether you take this point or you take this point, distance from the origin is root 2. Okay. And the radius of the circle is 3. So, all the three singularities of f z equal to e to the power z t over z square into 2 z plus 2 lie inside C. Okay. Okay. So, we have let f z be equal to e to the power z t upon z square into z square plus 2 z plus 2. Okay. So, at z equal to 0, f z has a pole of order 2. And at z equal to plus minus minus 1 plus minus I, and at z equal to minus 1 plus minus I, at z equal to minus 1 plus minus I, it has simple poles. See, z equal to if you multiply f z by z square and take the limit as z tends to 0, you get what? Limit z tends to 0, z square times f z gives you so e to power z t becomes e to power 0, that is 1 upon 2. Okay. So, it has a pole of order 2, and at z equal to minus 1 plus minus I, the denominator has simple zeros. So, we f z has simple poles. Now, let us find the residue at each of these points, because all the three singularities, singularity at z equal to 0 and z equal to minus 1 plus minus I lie inside C. Okay. So, first we find the residue at the simple poles, residue at z equal to minus 1 plus I, okay, of f z we can find. So, this is equal to e to the power z t. Now, in this case we can even so we can write z square into z. Let me write one root as z 1, the other root as z 2. Let us say z 1 equal to minus 1 plus I and z 2 be equal to minus 1 minus I. Okay. So, z minus z 1 into z minus z 2 I write for z square plus z 2 z plus 2, and here I multiply this by z minus z 1, okay, and take the limit as z tends to z 1. Okay. Z 1 I take as minus 1 plus I. So, this will be e to the power z 1 t, okay. This cancels with this, divided by z 1 square into z 1 minus z 2. Okay. Now, z 1 minus z 2 is equal to 2 I. Okay. So, this is e to the power minus 1 plus I into t divided by z 1 square. Z 1 square is minus 1 plus I whole square. So, this is 1 plus I square. So, 1 minus 1 minus 2 I. So, we get minus 2 I. So, minus 2 I into z 1 minus z 2 is 2 I square is minus 1. So, this is 1 by 4 e raised to the power minus 1 plus I into t, and residue at z equal to minus 1 minus I similarly will be limit z tends to z 2 e to the power z t into z minus z 2 divided by z square into z minus z 1 z minus z 2. This cancels and we get e to the power z 2 t into z 2 square z 2 minus z 1. So, z 2 is minus 1 minus I. So, e to the power minus 1 minus I into t divided by z minus 1 minus I whole square, and we get z 2 minus z 1 as minus 2 I. So, this is e to the power minus 1 minus I into t over this 1 plus I whole square. So, 2 I into minus 2 I, and what we get is 1 by 4 e to the power minus 1 minus I into t. So, we found the residue at z equal to minus 1 plus I and minus 1 minus I. Now, let us find the residue at z equal to 0. So, residue at z equal to 0 of f z will be equal to because it is a pole of order 2. So, 1 over 2 minus 1 factorial limit z tends to 0 d over dz of z square times f z. So, e to the power z t divided by z square into z square plus 2 z plus 2. So, this will cancel, and now we have to differentiate this expression with respect to z. So, limit z tends to 0, and what we get e to the power z t when you differentiate with respect to z, e to the power z t into t we get, and then we get z square plus 2 z plus 2, and then we get the derivative of z square plus 2 z plus 2 is 2 z plus 2 into e to the power z t divided by z square plus 2 z plus 2 whole square. So, when you put z, let z go to 0 means e to power z t goes to 1, then here we get t into this is 0, this is 0, 2. So, 2 t, and here we will get minus 2 because this is 0, this is 2, and this is e to power 0. So, 1. So, and then denominator is 2 square. So, 4 we have. So, t minus 1 by 2. Okay. Now, we add all these residues, okay, because the value which we have to find is the value we have to find of 1 over 2 pi I integral over c f z dz. Okay. So, this is nothing but sum of residues at z equal to 0 and z equal to minus 1 plus minus I. So, this is equal to t minus 1 by 2, okay, and then we have here 1 by 4 e to the power minus 1 minus I into t. First we write this e to the power minus 1 plus I into t plus e to the power minus 1 minus I into t. E to the power minus t we can write outside. So, this is t minus 1 divided by 2, then e to the power minus t, and inside we get e to the power I t plus e to the power minus I t, okay, e to the power I t plus e to the power minus I t. Okay. So, this is t minus 1 divided by 2, and then we have 1 by 4 e to the power minus t into 2 cos t. This is 2 cos t. Okay. I am treating t as a it could be even a complex number. Cos z is e to power I z plus e to power minus I z. Okay. So, this is nothing but t minus 1 by 2 plus e to the power minus t cos t by 2. So, this is t minus 1 plus e to the power minus t cos t divided by 2. This is the answer. Okay. So, this is how we find the this contour integration. With this I would end my lecture. Thank you very much for your attention.